Now in this section we'll be looking at permutations, and permutations of a set are basically just a unique ordering of the elements for that set. So for example, ABC would be a different permutation than CBA even though they contain the same elements. And the number of permutations of a given set is just the number of unique ways the elements of that set can be ordered. So if we look at some quick examples, we'll say, how many ways are there to order n elements in a set? And we'll kind of rely back on our basic counting principle. Let's look at an area that has even more events than what you see here. And let's just say that there are n total events, n total elements within the set omega. Well, if we want to simplify this, then we can say that we're just taking every one of those n elements and putting them into a bucket. So the question that we have to ask first is, when we're placing the first element, how many unique elements are available? How many options do I have at this first stage? And well, the answer is that I have n options. Now, when I go to my second stage, how many options do I have? Well, I've removed one. I did that in the first stage. So now I have n minus 1. When I make it to the third stage, I'm going to have n minus 2, then n minus 3, n minus 4, so on and so forth, all the way down until I make it to my very last stage. And so there may be many, many more stages in here that we don't see. But when I make it to that very last stage, I only have one element left to place. And so the total number of options for the element that I can place there, the total number of available options, is really just 1. And so what we're left with is n times n minus 1 times n minus 2 times n minus 3 times n minus 4, all the way down until we reach 1. And for those of you that recognize this sequence, you might be saying that looks familiar. And that's because it should look somewhat familiar. What we're left with is what's called n factorial. And n factorial is exactly this sequence. It's n times n minus 1 times n minus 2 times n minus 3 multiplied all the way down until you reach 1. So what we say is that the number of permutations of n, when there are n elements, is just equal to n factorial. If we look at a practical example here, let's say that there are n equals 3 elements in our set. Well, we're going to first take n, which is 3, and then multiply that by n minus 1, which is 2. And what do you know? Now we're down to this very last one, which is 1. And so we end up with 3 times 2 times 1, which means there are 6 unique ways or 6 permutations of a set with 3 elements. Now, let's try and identify what those are. If we say that we have elements A, B, and C in our set, then one permutation might be A, B, C. Another permutation might be A, C, B. Then B, A, C, B, C, A, C, A, B, and C, B, A. And if you can come up with another permutation than that, then I don't know how you did it, because those are the only 6 ways to order those 3 elements. Again, making sure that we include all of the elements in that. So permutations, again, are the number of ways to just order the n elements. So all n elements must be included, and that is equal to the number of elements as a factorial, or n factorial. Now, the next question that we might ask is, how many subsets of a set of n elements can we create? So let's assume that we have some elements hanging out over here, and they're all just living in their fancy space that we call omega. Now, the question that we'll ask is, how many different subsets are there? As you may recall, a subset is any possible combination of those elements, whether they're there or not. And so a way to look at this is really as a binary decision tree. We're going to go element by element from element 1 to element 2 to element 3 and just say, do we include it or do we not? And we'll call those a 1 or a 0 state. Is it in or not? And we do that for every element. And so what we're left with is really just a 2 raised to the power n. And while that may seem overly simple, that's the answer. It is just 2 to the power n. Because for every element of those n elements, we have 2 options. So we would say if we have a set of 3 elements, so let's just say n is equal to 3, that there are 2 raised to the 3, or 8 possible subsets of the set of n elements. Now, if we want to look at a practical example, let's say that we're looking at a set of 2 elements. So our n is just equal to 2. And you might be asking, well, how many subsets of that can you create? And the answer, based on our estimation here, or based on our hypothesis, is that there are 4 possible subsets of a set of 2 elements. So let's call our elements A and B. Well, how many subsets can you create? You can create a subset that is the empty set. You can create the subset that is A. You can create the subset that is B. And you can create the subset that is A and B. And in the case of subsets, order doesn't matter. So we have shown here that there are 1, 2, 3, and then 4 possible subsets for a set of 2 elements, which again just shows that our 2 to the n hypothesis works in the case of 2 elements, and it works in the case of more than 2 elements as well. Now, another question you might ask is, how many unique proper subsets of a set of n elements can we create? And if we look back at our previous slide, you'll notice that we did include the empty set as well as the set of the elements itself. And our definition for proper subsets is a subset that is not equal to the set itself. So in this case, the answer just very quickly is 2 to the n minus 1, subtracting off that set that, or that subset that is the set, so that we are left with only proper subsets. Now, the next thing we'll look at is what's called an R permutation. So we looked at permutations earlier and said that that is just n factorial. But an R permutation takes things a little bit differently. Instead of saying how many permutations of the same length as the original set can I make, we're going to ask the question, how many unique orderings of a subset of the set can I make with a defined length, with R elements? So we're looking at how many unique orderings that are R elements long can be made from a set with n elements. And it should be pretty self-explanatory, but in this case, if we are selecting R elements, then n must be greater than or equal to R. So to look at this, let's say that we have a set that is called X, and X has 3 elements in it, and those are going to be A, B, and C. And let's say that we are trying to create an R permutation where R is equal to 2. And again, these are the unique orderings. And what we'll find is, just looking at X real quick, we'll say that n is equal to 3 as well. And so in this case, the number of unique orderings of a 2-element subset of X is going to be A, then B, A, then C, B, then A, B, then C, C, then A, and then C, then B. So you'll notice that there are 6 total permutations available. What we really need to do is eliminate the number of sets that aren't left. If you remember, we looked at the proof of a permutation and said that it's just n times n minus 1 times n minus 2 all the way down to 1. Well, in this case, when we're selecting, we no longer have options for all of these, because in the case where n is 3 and r is 2, we take this option and this option, but then we ignore all of the rest of this because we're only selecting 2 elements. Now, to put this mathematically, we would say that this value down here is really just n minus r, because this value is r. I'm selecting 2 elements. So this area is n minus r. So if we recognize that we're multiplying here and we want to remove this n minus r factorial, then all we have to do is divide it out. And so what we'll find is that for an r permutation, the number of r permutations from a set of n elements is just equal to n factorial over n minus r factorial.